Welcome back to section 1 of topic 3. So we have a little understanding of energy and light, talking about the anatomy of a wave and looking at the light equation. Continuing on, we're now looking at the electromagnetic spectrum. Remember that light is essentially electromagnetic waves. And so the electromagnetic spectrum just shows the different types of light based on wavelength and frequency. In the last video, we looked at the equation of light as C equals wavelength times frequency. And we talked about how these two variables have an inverse relationship. So as the wave gets longer, the frequency gets smaller, and vice versa. When we take a look at the electromagnetic spectrum, we will see why that is. So what we see in the video here, or the screen here, are the different types of light. All light waves travel at the same speed of light, but not all light waves are the same. Over here on the left are these waves that are of the shortest wavelength. They are very, very, very short. And so the shortest wavelengths on the spectrum are gamma rays. A little bit longer are X-rays, and a little bit longer still are ultraviolet or UV rays. Now we're going to skip this section for a second. Let's go past that. A little bit longer still is our infrared waves, then microwaves, and then radio waves. And radio waves, a quick note about that, a lot of times people get confused because they think radio is sound. But think about, how do radio stations transmit music over the air to be received by our radio stations? It's actually light waves, and it's not until it gets brought down and converted into sound that it actually is something we can hear. So those are 6 types of light. The 7th type is the little tiny region of space right here known as visible light. And this is actually the only region of the electromagnetic spectrum that we as humans can see. This is where our colors come from. A little bit of information. You don't have to memorize specific numbers about any of these, but the one thing I would like you to know is I would like you to know relatively what are the wavelength regions that the human eye can see. And so if you think about your colors of the rainbow, Roy G. Biv, if you will, violet is over here. Violet is approximately 400 nanometers. And red over here is approximately 700 nanometers. That is the only range of light that we as humans can see. If the wavelength is any smaller than 400, it gets into the UV region and we can't see it. If it gets longer than 700, it gets into the infrared region, and we can't see that either. So, as a review, how many types of light waves are there? How many regions? There are 7. Of the 7, the only ones we can see is the visible light region. Now, question, which of the 7 regions does light travel the fastest? The answer is none of them. They all travel the same speed of light. Gamma rays and radio waves are both light waves, and they will travel at the same speed of light, which is c. But their wavelength and frequencies will not be the same. You can see that the gamma rays have the shorter wavelength, and so therefore smaller wavelength would mean a higher frequency. On the other hand, radio waves would have a very large wavelength and thus a very small frequency, because they both have to equal the speed of light. And so we see that up here. It shows that as wavelength increases going to the right, frequency must then increase going to the left. We are going to get into this a little bit later, but it's a good opportunity now to point out how energy relates to all this. We are going to see how energy increases in the same direction that frequency does. Why that is, we'll talk about later, but for right now, it's good to point out that the relationship between energy and frequency is a direct relationship, meaning they're both going to increase in the same direction. So if we look at a situation where the wavelength is decreasing, that must mean frequency and energy both increase, and vice versa. All right. Let's look at a few examples so we can see how to use that light equation that we've been looking at. So let's look at example 1 in your notes. 2 electromagnetic waves are represented below. We have wave A, which is 714 nanometers, and wave B, which is 503. Both of them are in our visible light spectrum. You'll notice, 714, it's getting to the area where it might not be seen by some humans, but relatively that's our red threshold. Nevertheless, the question is asking, what is the frequency for wave A and wave B? All right, so looking at our speed of light equation, or just simply our light equation, we are asked to solve for frequency, which is our letter nu. So what I like to do is I like to actually rewrite the equation in terms of what I'm solving for. So all I did was just rearrange the equation to be set up to solve for nu. And now I plug in my information. The speed of light is 2.998 times 10 to the 8th meters per second. And by the way, I believe that number is on the back of your periodic table. Divided by the wavelength. Now the wavelength is given as 714, but it's in nanometers. I can't plug in nanometers because then it won't cancel out with the meters. So we're going to need to do a metric conversion. As a reminder from topic 1, 1 nanometer is equal to 1 times 10 to the negative 9th meters. Or another way to think about it is there are 1 times 10 to the 9th nanometers, a lot, in 1 meter. However you decide to convert is fine, but here's a trick. Here's a really easy way to convert. This is what I do. So 714 nanometers. Remember, what does nano stand for? Simply replace nano with what nano stands for, which is times 10 to the negative 9th. And that's it. Notice I did not change the number. I still plug in 714. But then just simply add on times 10 to the negative 9th. And that actually will convert it to meters for me. So now when I divide, the meters will cancel, and I will end up in units of 1 over second, which is the same thing as hertz, which is my frequency. So let's solve. I'm going to plug this in as 2.998 E8 divided by 714 E negative 9. Make sure you do negative 9 and not the subtraction symbol 9. And if you calculated that correctly with 3 sig figs, looks like my answer is 4.20 times 10 to the 14th 1 over second, or you could just simply say hertz. Go ahead and try wave B on your own. Pause the video and then hit play to reveal the setup and the answer. Alright, here's our setup for the second problem. We have the speed of light on the top. On the bottom, we have the wavelength converted to meters, just like we did before, and still keeping 3 sig figs because that's my lowest number. My answer is 5.96 times 10 to the 14th, and this time I wrote hertz rather than 1 over second, just so you can see that either one is fine. They're both the same unit. Alright, let's look at example 2. Very similar to before, but this time we're solving for a wavelength. What is the wavelength of a purple light that has a frequency of 6.88 times 10 to the 14th hertz? So this time, if my equation is C equals wavelength times frequency, I'm going to rearrange it to solve now for wavelength, which will then be C divided by frequency. So wavelength is going to be 2.998 times 10 to the 8th meters per second divided by, frequency, which my frequency is in hertz, which is, that's the unit I need it to be, so there's no conversion I need to do. 6.88 times 10 to the 14th. Rather than write hertz, I'm going to write 1 over second. That way you can see that the seconds cancel. And so when we get our answer, it's going to be in unit of meters. So keep that in mind. So let's solve that. 2.998 E8 divided by 6.88 E14. And I end up getting, with 3 sig figs, 4.36 times 10 to the negative 7th. Now remember, it's reported in meters, right? Because that's what the unit is going to be left with when I cancel everything out. But do we usually represent wavelengths in meters when we're dealing with visible light? No, we usually see it in nanometers, right? So even though the problem didn't explicitly say put the answer in nanometers, it should be practice that when we are reporting wavelengths for colors, we want to convert it to nanometers, right? So we can do that by a simple metric conversion. And if you do it a different way, that's totally fine. You can do it however you'd like. But we can set it up like this. We can say 1 meter contains 1 times 10 to the 9th nanometers. Notice it's times 10 to the 9th, not -9th, because think about it. A nanometer is so much smaller than a meter. So it would make sense that 1 meter contains a heck of a lot of little tiny nanometers. Another way you can write it, whichever way makes more sense for you, is you could write it how we learned in topic 1, which is saying, okay, what is 1 nanometer equal to? 1 nanometer is saying the same thing as 1 times 10 to the -9th. So in this case, the -9th will go on the bottom. To be honest, I don't care which method you use because they're both going to give you the same answer. It just depends on what makes more sense to you. Either way, no matter how you did it, you should end up getting the answer as 436 nanometers, which doesn't that make sense because we know the visible light spectrum is between 400 and 700 nanometers. So that lines up. All right, last example here for the video. Compared to ultraviolet radiation, infrared radiation occurs at blank wavelengths, blank frequencies, and blank energies. So this problem is testing whether or not we know the relationships between all the variables. So as a reminder, let's remind ourselves that these are the three variables we're going to look at. We're going to look at wavelength, frequency, and energy. And I have down here the electromagnetic spectrum again, just so we can refer to it since we're still learning. The question is asking us to compare ultraviolet radiation with infrared radiation. So it says compared to UV, answer the following questions about infrared. Infrared would occur at, well, let's first talk about their wavelengths. Does infrared have longer wavelengths or shorter wavelengths? Infrared has longer wavelengths. And so I'd write longer. And keep in mind that wavelength is bigger for infrared. So I'm going to draw a little arrow up indicating the wavelength would be higher for infrared. If wavelength is higher for infrared, that means it must be smaller or lower for frequencies because there's an inverse relationship. And remember, whatever frequency does, so does energy. So energy will also be lower. So infrared waves have lower energy than UV. All right, that wraps up section 1. We'll see you in section 2.